the process is considered heating. Okay, so it's now a heated. So basically, it is a heating process. Okay, until the pressure is 600 kilopascal. So you can write here the next pressure after the heating is 600 kilopascal. Okay. Okay. If you look here, this is a rigid container. For the second state, the only information is pressure. So you need another information in order to solve the state 2. Okay, because in the state 2, they ask you to calculate the temperature and the total enthalpy when the heating is completed. So the question is, first question. So the question Q1, find temperature and the total enthalpy at the initial state. Find the T1 and total enthalpy. Total enthalpy is a capital H. Okay, is in unit kilojoule. Okay, while the second part, which is Q2, they ask you to find T2, because after the heating process completed, okay, find T2 and the total enthalpy, okay, which is H2. Okay. So we solve this one by one. Okay, first we need to find the phase 1. Okay. So how to find the phase 1? Okay. You need two intensive properties. Okay. So the first properties, of course, you have the pressure, P1, 300 kilopascal. Okay. And then you need a second intensive properties. Okay, what intensive properties that you can obtain from the current information? You have the mass. The mass is not intensive. You got a volume. Again, volume also not intensive. But you can find the specific volume. Okay. You can find the specific volume if you divide the volume divided by mass. But you need the volume is in meter cube divided by kilogram. Okay. So you need to convert the 14 liter to the meter cube. How much? I think if you do with some calculator, 1 liter equals to 1000 milliliter, and then 1 milliliter equals to 1 centimeter cubic. Okay. You can use okay, 14 liter. Okay, let's say we do it one by one. 14 liter. So 1 liter equals to 1000 milliliter. Okay. So you cancel the liter, and then you 1 centimeter cubic equals to 1 milliliter. So you cancel the milliliter. Okay. And then this is centimeter. So you need a 1 meter equals to 100 centimeter. Okay. So this is cubic. So this is to the power of 3. Okay. So centimeter cubic cancel out. So 14 multiplied by 1000 divided by 100 to the power of 3. Okay. Because 100 is you want to change to the cubic. So you need to the power of 3. So how much this? 14 times 1000 divided by 100. Um, so if you already sorry, if you are already calculate, you can share in the chat box. Okay. 0 point okay, 0.014 meter cube. Okay. So that is volume in meter cube. So you can find, I put it here. So V1 equals to V divided by M, V1 divided by M1. So V1 is 0.014 divided by M is 10 kilogram. Okay. So 0.14, is it correct? Or 0.0014? Um, so this is wrong. Yes. Thank you, Adam. 0.0014 meter cube per kilogram. So this is your V1. Okay. So that is your V1. So if we can put back the information, okay, for the phase one, so phase, sorry, for the state one, you have P1 300 kilopascal and specific volume 1 0.0014 meter cube per kilogram. Okay, then you can find the phase. Okay, so you have two intensive properties. So what you can do, like yesterday, okay, at P equals to 300 kilopascal, okay, since you have the V, so you need to find what is the VF and what is the VG at 300 kilopascal. So that you need to know whether the given specific volume V1 is smaller than VF or in between or larger than VG. So it's the same like yesterday when we do it for water. Okay. So in this case, you need to use table what? Which table? Table for the refrigerant, but pressure based because you have the pressure information. Um, okay. So if you go to the, so you need table A A12. Okay, this one, pressure table. So you go to the table A12. Okay, so A12 is a bit far down. A11, A12. Okay, so this is the pressure. Sorry, this is a table A12. Okay, so A12. So you need the 300 kilopascal, right? 300 kilopascal. So you need to find 300. Huh, 300 kilopascal. Okay. Huh. Mm, so seems there is no 300 kilopascal. How come you have to do interpolation? 300 kilopascal is in between. Is it? This is for refrigerant. Yeah. Okay. Make sure you check the right table. Okay. So this is for refrigerant. So you need the 300 kilopascal. Okay. So 300 kilopascal is in this range. Okay. 300 kilopascal is in between. Uh, why there is some off to my pen. Really. Why? Okay. Okay. So 300 kilopascal is in between this value, and then you need this two value for the VF, and this is two value for the PG. Okay. So this is your VF, this is your VG. So your value is between this 300 kilopascal. So if you look, 300 is in between 280 with 320, and you need this VF in between and VG in between. Okay, so um, so you need to take both data. Okay, so since the value is in between, so you need to do a simple interpolation by divided the data into two. Okay, okay. So VF, I need to it's too small. Okay, so for the VF, so you need to divide into two, 0.0007699 plus 0.000777 divided by 2. Okay, so that is for the VF, and for the VG you have 0.0723 by 2 plus 0.063604. Okay, and divide by 2. Okay, how much the VF? I think is in between 0.0000. This one is still a 7. Is it 7? Yes. 7, 7. Can someone calculate both VF and VG? 0.00 plus 0.7. Okay, thank you, Ayman. 77355 meter cube per kilogram. So that is for VF, okay? And for the VG, um, 0. Okay, thank you, Ashraf. 0.067 978 meter cube per kilogram. Okay, so if you compare the value with V1, so this is your V1, okay? So the value is what you can see, VF is very small, and VG 0.06, which is a bit larger than V1. So you can see that the V1 is between, correct? VF and VG at 300 kilopascal. Okay, so meaning that your phase,
Mix.
so the phase one is a mixture, saturated mixture. Okay, is in between. Okay, then you got the phase. The question is find the temperature. Okay, so for saturated mixture, the corresponding T is equals to T saturation at P given. Okay, so meaning you have to find T saturation at 300 kilopascal. Right? Because P given at 1 is a 300 kilopascal. So you find 300 kilopascal. So you need to find this temperature. Okay, this temperature is in between these two. Okay, so remember this is refrigerant. So the temperature is a bit uh, small or low because this is not water. Okay, so the T saturation equals to negative 1.25 plus 2.46 divided by 2. Okay, how much? Should be 1 point something, right? Or negative. So negative 1.25 plus 2.46 divided by 2, oh, 0.6. Okay, correct. Thank you, Ashraf. Amen. 0.605 degree Celsius. Okay, so this is your T1. Okay, so that is your T1. Okay. How about H? Okay, you need to find the enthalpy. Okay, the total enthalpy. If you look, you need to find the H1. Okay, how to find H1? You need to, okay, I think I need some more space here. Oh, because more space here. How can I increase this? So for H1, is actually a mass 1 time H1. Okay, you got a mass 1, but you don't have a H1. So how to find H1? So H1 is you need to find from the quality, because for saturated mixture, okay, remember for the saturated mixture, for saturated mixture, to find other properties, we need X. Okay, we need X, which is we need the quality, because it is saturated mixture. Okay, so how to find X, or in this case it's X1. So you have the VF, right? So you can find V1 minus VF divided by VG minus VF. Okay, it's a bit uh, a lengthy calculation, because you need to do it one by one. Okay, I think V1 we already know uh, from the calculation. Where is the V1? Yeah, this one. Okay, so V1 is 0.0014. Okay, 0.0014. Okay, to 0, right? Okay, and VF, okay, VF is a bit longer. This is 1, 2, 3, 4, 7.73 times 10 to the power of 4 minus 7.735 77355 times 10 to the power of negative 4. Okay, divided by Vg minus Vf. Vg is how much Vg? 6.7978 times 10 to the power of 2. 6.7978 times 10 to the power of negative 2 minus 7.7355 times 10 to the power of, okay, what is the x1? I think you need to a bit careful in terms of to the exponent to the power of uh, 10, so that you not miss the or you don't do the careless mistake when you pressing the calculator. 0.009. It's very small, Ashraf. How about others? You got the same value? Same, okay. So 0.009. Three two two. Okay, right. I think I need to open the. Okay, so this is your x1, x1 0.009322. Okay, so so to find the H1, I need to. So find H1, so you can use HF plus X1 HFG at 300 kilopascal. Okay, so we need to find the HF and HFG at 300 kilopascal. Okay, so what is HF? I think we need to do again the HF. So we find the HF column. Okay, remember 300 kilopascal is in this line. Okay, I just write down the line of 300 kilopascal. So you need this HF and HFG. So this is your HF, this is HFG. Okay, so your HF here, 50.18 plus 55.16 divided by 2. Okay, while HFG 199.54 plus 196.71. 196.71 divided by 2. Okay. I think the value is close to the 50. Okay, thank you. HF is a 52.67 kilojoule per kilogram, while HFG is a 198.125 kilojoule per kilogram. Okay, so you can based on these two value, you can put back the calculation of H1. So H1 equals to HF plus X1 HFG. So HF is 52.67 plus 0.0, what is the value? 0.09322. Okay, 9322. Okay, multiply by HFG 198.125. So that is your H1. I think it is close to the HF. It's about 53 or 54. So if you calculate 198.125 multiplied by plus 54, is it? 54, okay, thank you, Shah. 54.5, I make it a 2 decimal point, 52. 54.52 kilojoule per kilogram. Okay, so that is H1. Why, Anik? You have any question? Same. Okay. Then for the total enthalpy, because we want to find the total enthalpy. H1 equals to M1 times H1. So M1 is 10 kilogram. H1 is 54.52. So basically you got 545.2 kilojoule. Okay. So that is a total enthalpy. 50. Okay, so that is the first part. So you complete the calculation of properties for the first part. And then if you look, you need find the T2 and H2, the second part. Okay, so if you looks to the problem, okay, the only information, okay, if I write again the first, okay, you have P1 300 kilopascal, you got a P2 600 kilopascal, you got V1 14 liter, you got M1 10 kilogram. Based on the calculation, you got V1 equals to 0.0014 meter cube per kilogram. Okay. Okay. So, this is a heating. Okay. So you need another information from the okay, from the problem in order to define the phase, because for the phase 2, what is the, we need to find what is the phase 2. Okay, so same thing like phase 1, we need another intensive properties. Okay. What is the information that you can extract from the problem? So you know that this system is a rigid container. Okay. So they are using a rigid container. What meaning by the rigid container? So rigid container means the volume is constant. Okay. So the volume is not changing. The boundary is maintained as it is, as the initial state. So V2 equals to V1. Because of the volume is a constant, and uh, rigid container is a consider a closed system. So for the closed system, you are not allowing any mass going in or going out. So mass 2 is also equal to mass 1. Okay. So normally for the rigid container, you can say that, okay, for the rigid container, this will relate to the volume is a constant, M is also constant. Okay, so basically the specific volume 2 will be equals to specific volume 1. Okay, so specific volume 2 is equals to specific volume 1. My volume is not really. So V1, okay, which is V1 is equals to V2 equals to V1 equals to 0.0014 meter cube per kilogram. Okay, so now you have two information of intensive properties: 600 kilopascal, okay, 600 kilopascal, and the specific volume. So you have the P2 600 kilopascal and specific volume to 0.0014 meter cube per kilogram. So we check again, same. So at 600 kilopascal, how to define phase? You need to find the VF and you need to find the VG. Okay, hopefully this time we don't need to do some interpolation. Okay, yes, there is no. Okay, so this is the pressure. I think we are using the same table, A12. Okay, for the pressure. So you find the 600 kilopascal. So there is a 600 kilopascal here. So this is your VF. This is your VG. Okay, so this is your VF. This is your VG. So you can uh, take the value directly. Okay, so 0.008199 meter cube, and for the VG 0.034295, 0.034295 meter cube per kilogram, meter cube per kilogram. Okay, so if you look, so what you need to do next? So compare V2 versus VF and VG at 600 kilopascal. Okay, so you compare this value 0.014. So basically it is larger than VF, smaller than VG. So V2 is in between VF and VG. So the phase 2 is a saturated mixture. Okay, so phase 2 is also saturated mixture. phase one is a saturated mixture. Okay. So what is the question is they ask you to find T, right? Okay. So for saturated mixture, T2 will be T saturation at T given. So same thing. Uh, this is at P given. That means T saturation at 600 kilopascal. Okay. Previously is 300. So you need to find T saturation at 600 kilopascal. So at 600 kilopascal, the T saturation just next to the pressure value, this one, saturation temperature. So the second column, so this is your value. So 21.55 degrees Celsius. Okay, 21.55 degrees Celsius, this value. So that is a T2, okay? And then you need to calculate again for the H2, okay? So in order to find the H2, you need to find H2, small h2, which is H2 equals to H2 multiplied by M2. Okay, you know that M2 equals to M1, which is 10 kilogram. But how to find the H2? So you need to know what is the X2 because it is a saturated mixture. So you need to find the quality. So how to find the quality? I think the same like the previous step. So X2 you can find by calculating from the V2. Okay, this one is at 600 kilopascal. Okay, so once you can find the X2, then you can find H2 using the equation of HF plus X2 HFG at 600 kilopascal. Okay, so then you can find the H2 by multiplying M2 with the H2. Okay, all right. So I think you can continue the exercise until you get the value. So basically, this is the method of how to solve the thermodynamic problem using the refrigerant. So what I can say, the approach is the same like water. The only difference is the table. Okay. You might thinking about, are you really use the table when you are working? Okay. So basically, you don't use a table actually. This table properties, okay, where is the table? Yeah. This table is only for your understanding how the data tabulated in terms of a table. Yes, if you are working in the certain industry, some of the industry use the table, but majority of the industry they are not using table anymore. They are using some system that can be apps that can be described by using some digital database. Okay, let me find one database for the water. Okay, So if you look, okay, this is one example of table properties that can be accessed from online. Okay. So same thing, this is a different temperature pressure. Um, but I want to show you some way of calculating or to check. Okay. Thermodynamic. Okay. So if you can explore, okay, okay, this is one software that used to calculate property directly. Okay, for example, okay, um, okay, this if I can, you can download as well the apps that can calculate the table property. Let's say you don't want to do some interpolation because this is very tedious. Okay, you can find from the any website or any apps that can calculate the table properties. Okay, but the only thing is this table sometimes not really accurate. Okay? Let's say we try at let's say we try to calculate we take some new data. Okay, let's say we need to find the water at 100 kilopascal, 200 degrees Celsius. Okay, so we take from the, okay, so 100 kilopascal. So I put here 100 kilopascal and 200 degrees Celsius. Okay, we calculate, or they only give us the phase. Okay, if you look here, the medium is vaporous, not liquid water. So they only give you the phase. They're not giving you some properties. Probably we have to pay. I don't know. Okay. Um, this should be can be calculated, but I don't know why it is not. Okay. Okay. It is a superheated. Okay. Overheated steam. Upper limit. No. Okay, never mind. Later, if I can find one or good table properties from the online, I will share you in the class. Okay. So, what I want to say that in the real industry, some of the industry they use tabulated data electronically. Okay, they don't use a table like this one. But in order to understand how the data is tabulated, how the data is obtained, it is good if we can learn from the basic, and then we can know how to define the phase, how to define the other properties based on the information. Okay. Okay, next one, we need to move to the last part of the topic, which is related to the ideal gas equation. Okay, so if we can recall, okay, we have covered the uh, water. Okay, we have covered the refrigerant. One example. I think the rest you can do example that I'll share it later. Okay, so working fluid in system. So we have learned the water properties. We learned about the refrigerant properties. Okay, even though we're not doing much example, can do it later. And the third one is the air or gas. Okay, so what you can see, in order to solve a water properties, we need the table. For the refrigerant properties, again, you need the table. But for the third working fluid, you need the ideal gas equation. Or you need equation actually. You need equation. You don't need a table. Okay. So that's why the last part of the topic for this chapter, we need to learn, or we need to understand the use of ideal gas equation in order to solve a problem of gases. Okay, I think this ideal gas equation is commonly you have used it before when you studying physics. Okay, so what is the ideal gas equation? So it is simplest and the best known equation for a substance in a gas phase. Okay, in a gas phase. So this is the simplest and the easiest equation. Okay, this equation used to predict the PVT. What is PVT? Pressure, volume, temperature relation. Pressure, volume, and temperature relation of a gas. Okay. So what is the ideal gas equation? This one. PV RT. This is a specific volume. So if you look here, PV RT. What is P? P is pressure, is in kilopascal. V is a specific volume, is in meter cube per kilogram. T is the temperature, is in Kelvin, and R is a gas constant. What is a gas constant? Is the properties of gas. Okay, kilojoule per kilogram Kelvin, the unit. Okay, so this is example of gas constant for several gas that you might dealing with. Okay, so for air, the gas constant is 0.287 kilojoule per kilogram Kelvin. Okay, helium 2.0769. Okay, I think if you don't use a gas constant, let's say you don't know the gas constant, you can change the gas constant to terms RU. Okay, gas constant can be calculated if you know the universal gas RU divided by M. M is a molar mass, is a molecular weight of the gas. Okay, for example, hydrogen, the molecular weight is 1. Okay, oxygen, the molecular weight is 16 something. I think where you can get this information, you can refer to the table A1. Table A1. Because table A1 is data for gases. Okay. If you go to the table, this one, table A1, gas constant and molar mass. Okay. So you can see here. So this is the gas constant and this is the molar mass, the molecular weight of the gas. Okay, for hydrogen, it should be 1. Is it? Where is hydrogen? Oh, sorry, 2. Why 2? Because of H2. 1 if it's only hydrogen, but for the gas hydrogen, it's a 2. 2.016 to be accurate. Okay. So where to use, how to use, this is molar mass, this is the gas constant. So most probably you use a gas constant because you use a PVRT. Okay. Or if you don't want to use V, PV divided by MRT. So if you bring the M to the right, PVMRT. So I don't know whether you are familiar using either the first one or you are using the third one. Okay. So one is with mass, another one is without mass. Okay. Term mass. Okay. But both is the same. Okay. So so to solve any problem using gas, so you need to use ideal gas equation. Okay. So this is other representing of other equation in the other form. Okay. So if you are comparing between two state, okay, with a fixed mass, okay, so you can use this equation. How the equation come? Basically using PVMRT or PVRT. So you bring the M. So M equals to PVRT. So for the mass fix, M1 equals to M2. So P1 V1 RT1 equals to P2 V2 RT2. So since the gas is a constant, the gas is the same, so the R is cancelled out. P1 V1 P1 equals to P2 V2 V2. This equation is quite commonly used when you are dealing with same gas and different process with constant mass and volume, or constant mass, sometimes constant mass. Constant volume can be changed as well depending on the situation. Okay. So for the gas, it's a bit easy because you only use PVMRT. So you don't use any table anymore. Okay, you don't use table to define the properties for the gases. Okay, let's say we do some example here. Okay. Okay, this is some example of ideal gas. Okay, okay, there is some answer here. This is 1 meter cube tank containing air at 25 degrees Celsius and 500 kilopascal. Okay, so to solve the problem of ideal gas or gases, so you just need the ideal gas equation. Okay, so this problem is about 1 meter cube tank containing air at 25 degrees Celsius and 500 kilopascal. So you have a tank, okay? So the volume is 1 meter cube, temperature of 25 degrees Celsius, pressure is at 500 kilopascal. Okay, is connected through a valve to another tank. So this means this tank is connected to a pipe valve with another tank, okay, containing 5 kilogram of air. So both consist of air, but in this you got M equals to 5 kilogram, temperature of 35 degrees Celsius, and pressure of 200 kilopascal. Okay. Okay. To get more easy in terms of calculation, I put this is table tank A. This is a tank B. Okay. So this is not V1. This is VA, TA, and PA. So this is MB, TB, and PB. Okay. So what happened? The valve is open. The valve is open. Okay. And then the air mix from both tank. Okay. Until the temperature reach equilibrium. Until temperature reach equilibrium at 20 degrees Celsius. So this means T final. Okay, T2. Or T final. Probably this will be a bit confusing. I put a T final. Okay. Determine the volume of the second tank and the final equilibrium pressure of the air. Okay. First, you need to find the volume of the second tank. Volume of second tank, which is tank B. Okay. How to find the volume B? So, well, you just use ideal gas equation. Using ideal gas equation, PVMRT. Okay. So V volume, because you want to find the volume, V equals to MRT divided by P. Okay. So for the VB, you need to find MB RB TB divided by PB. So what is the MB? MB is given 5 kilogram. Okay. TB is given 35. PB is a 200 kilopascal. But what is the RB? Okay, this is air, right? This is air. So R for the air is equals to, from the table, we can find air, this one, okay, 0.287. Okay, R is 0.287 kilojoule per kilogram Kelvin. This is from table A1. Okay, so you just put everything back to the calculation. MB is a 5 kilogram, RB 0.287, TB is a 35. Okay, remember you must put in Kelvin. 35 plus 273 in order to convert into Kelvin. So that this one is in Kelvin. Divided by PB is a 200 kilopascal. Okay, why? Because this is in kilojoule per kilogram Kelvin. So I maintain the terms in kilopascal. So kilo and kilo. So everything will be cancelled out. So what is the value? VB 5 multiplied by 0.287 multiplied by this one is 5 0.287. This one is 35. So 2 3 308 divided by 200. So can you get this, the VB? Anyone get the, okay, thank you, Ashraf. 2.209 meter cube. Okay, right. 2.2099, okay, to be exact. Okay, also can. So basically it's close to 2.1 meter cubes, the volumes. Okay, and then find the final equilibrium pressure of the air. Okay, so how to find? I think okay, again you need to use uh, how to find the final equilibrium pressure. Okay, number two, you need to calculate the P2. Okay, so given only T2 is at 20 degrees Celsius. Okay, so you are using ideal gas equation. Still, you need to use ideal gas equation PV MRT. So to find the P2, you need the MRT divided by V. So M2RT2 divided by V2. So you got the T2, you need to find the M2 and V2. What is the M2? M2 is equals to MA plus MB, because when you open the valve, so you are mixing between the volume A and volume B, mass A and mass B, because this is extensive properties. You can add the volumes and the mass. How about the V? V2 is equals to VA plus VB. Okay, so basically you can find the equals to VA plus VB. You already calculate VB and VA is there. Then you need to do M2, which is MA plus MB. MB is given, so you need to find MA from the calculation of ideal gas equation for the A only. Okay. So next you can find the P2 by M2 R2. R is the same. R2 is RA. T2 divided by V2. So by right, you should can get the value of this 284.1 kilopascal. Okay. So what this problem indicate, whatever situation that dealing with the gas, you can solve the properties by using ideal gas equation, which is PV MRT or PVRT. Okay, so what I can say, the solving of ideal gas equation is a bit easier compared to the table properties, because you don't need to define the phase. You don't need to do the interpolation. It's quite straightforward for the gas, and it's much simple compared to the water properties or refrigerant properties. Okay, any questions? Okay, if there is no question, later I will share you some example of exercise on the ideal gas, so that you can do it for your improved understanding. Okay. So before we leave, probably I will share you the, let me share you the QR code. Uh,
Sir,
Yes.
can you give us the working calculation in WhatsApp group?
Which one?
The first example, the long calculation. The first one.
Okay. All right. I will print this one and share in the group. Yeah. For the first one, eh?
For the first one.
Okay. Where is the attendance? Okay, it's taking some time. Okay. Okay. So if there is no other question, I think that's all for today. Thank you very much. I will share the step for the long exercise this morning in your WhatsApp group. Okay, guys, thank you very much. I see you. Okay, tomorrow we don't have a class. Okay, I will remind again in the group. I will see you in the next week, and then I will give you some exercise for you to do a practice for understanding. Okay. Okay, thank you, and I see you again next week. Okay, bye. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera.
Thank you, Doctor.
All right.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor. Doctor.
Yes.